Thanks for coming back again for those that have subscribed. If you are yet to subscribe and you're new here, please click on the subscribe button and also the bell beside it to notify you when we drop our new video. Thank you. We want to consider Bernoulli's equation in this video. And what does it mean? What does this explain? Bernoulli explains or established a relation between the pressure in a moving incompressible liquid and the velocity of the flow. So when I say a moving incompressible liquid, I'm talking about a liquid that has low, very, very low viscosity. What Bernoulli's principle is talking about here states that if we have a moving incompressible liquid that has low viscosity, the work done, or let's say the pressure at every unit volume of the moving incompressible liquid plus the potential energy per unit volume plus the kinetic energy per unit volume all equals a constant. So that is what Bernoulli's principle is talking about. So let's take into consideration a pipe supplying water. So let's assume this pipe supplies water. So this pipe supplies water from a particular height, this, to the horizontal of this. So this is regarded to as before it reaches the ground, so we call that height 1. So why this is height 2. So, and then don't forget there is pressure exerted on each water molecule, and at the same time we have cross-sectional area for the water molecule. So we have this, we have this, we have this. So we are going to pick the point where we have the higher cross-sectional area. So let's assume this one is A2 and this one is A1. So between these points, let's say this is Y and this is X. So between points X, Y, we have the larger or bigger cross-sectional area at these points X and Y. So, and don't forget, we have, before we can have the cross-sectional area A2, the fluid must have traveled a distance L2. And here, before we can have this A1, the fluid must have traveled a distance L1. And at this particular point, the fluid flows with a speed or velocity. So we have velocity here, which is definitely high velocity. And a certain pressure is also here, which is a low pressure. So at a point where we have high velocity, definitely there will be lower pressure over there. So, and here we call that V2. So here we have high pressure. Why? Because the cross-sectional area is now wide, is now bigger. So we're going to have high pressure at this point and low pressure here because cross-sectional area is still relatively small at this point. So then we are going to have low velocity. Why? Because the cross-sectional area is larger now. So and at this point L1. So to determine the work done by the pressure, it is actually the pressure that is exerted on the fluid that enables the motion. And at the same time, when it flows out of the pipe, there is effect of a gravitational force felt on it. So we can actually determine the work done using work done equals force times distance. So, and however, the force exerted on the fluid is not ordinarily a force, it's a pressure. So we have to change this to the context of pressure. So, and don't forget, pressure equals force over area. So definitely force with what? Pressure times area. So we have pressure times area here multiplied by distance L. So if L is distance, area times distance will give us volume. So meaning the work done is equals to what? Pressure times volume. So we need to note this. So, and what Bernoulli's principle is explaining is that at every point of the liquid, there is a gain of kinetic energy, and at the same time, there is always a potential energy at every point, considering unit volume. So how can we consider the unit volume? So meaning that if this is a cross-sectional area travels over a distance L. So then that is a unit volume. So per unit volume of this flowing incompressible liquid, there is always gain in kinetic energy and potential energy. So how can we account for that? So since we are considering the potential energy gained per unit volume, so that potential energy will be given as, normally is mgh, but since we're considering mass per unit volume, which is density, rho, so potential energy per unit volume will be given as this. So where this is potential energy per unit volume. So then the kinetic energy per unit volume, which ordinarily is supposed to be half mv squared, will now be half rho half rho v squared. So this is the what? The kinetic energy per unit volume. Per unit volume of such liquid. So Bernoulli's principle now established the relationship. Now the relationship is between what the relationship is all about. That we have gotten, we derive an equation that from the principle that relates the velocity with the pressure. So what does it state? Like I said, the potential energy per unit volume plus the kinetic energy per unit volume plus the pressure at every part of a moving incompressible liquid. When you sum it together, all gives you constant. All is constant. So by the look of things, if I am to consider that according to what I have here, so meaning that the pressure at a given part of a moving incompressible liquid, or a given part of the velocity, plus the potential energy per unit volume, let me just call that PUV, plus kinetic energy per unit volume, all equals constant. The potential energy per unit volume plus the kinetic energy per unit volume and the pressure all equals a constant. This is in accordance with law of conservation of energy. Why? Because the energy at this point, the potential energy per unit volume, kinetic energy per unit volume, and the pressure at this point, the sum of which must be the same with what is at this point, because there is no frictional force to be overcome at that particular point, at each point of the moving incompressible liquid, since it is incompressible liquid. C. So the pressure here at this particular point, we have high pressure, and here we have low pressure. So we call that the change in pressure. So that is P2 minus P1 plus the potential energy per unit volume, which I have given as rho g h. So then becomes rho g into, we have two heights, which is h2 minus h1. So I have the h2 minus h1 plus the kinetic energy per unit volume, which I've given to be this half rho v squared, will now become half rho, then v, we have the velocity here and here. We're considering the 2 points anyway. So we have v squared, that's 2, minus v squared, that's 1. So all equals c. Don't forget c equals 1. So from there I can rearrange, and I have p1, that is p2 plus rho gh2 plus half rho v2 squared, all will equals to, all that are negative, we take them to the other side. So we have the p1 plus rho gh1 plus half rho v1 squared. So this is regarded as the Bernoulli's equation, so which can be used to find the pressure 1 or pressure 2 between two fixed points in a moving incompressible liquid. And however, the direction of the velocity must also be here in the diagram. The direction of the velocity is here, so, and it is a laminar flow. because the velocity does not changes over each other. So it maintains a uniform velocity all through. So this is a laminar flow. So this represents streamline represents the direction of velocity of the flow. Thanks for watching. Please subscribe to our YouTube channel. It's free. Thank you.